Hello and welcome. Today we have a linear algebra theorem. So this is the cauchy schwarz inequality. It states that if u and v are vectors on an inner product space V, then the inner product of uv squared is less than inner product of uu and vv. So we go straight to the proof. We begin with the basic stage. So if u is 0, automatically the inequality holds. So you can see that you will have uv squared. This will be 0, 0v, which is 0. But now u is also a 0v, which just gives you a 0. This is the left hand side. And the right hand side, you're going to have, which is 0, 0, which is just 0. And then now you have to multiply with the other part. But now this first is 0. So our value goes to 0. That's the induction stage. This is the right hand side. So if u is 0, it holds. But now that's not our main concern. So we go next to the next step. Now we are supposing that we don't want u to be 0. Neither do we want v to be 0. But now we are putting v to be is equals to ku, where k is a scalar. So what happens is we are going to substitute k wherever we have a v. So we prove the left hand side, because it's an inequality. The left hand side and the right hand side must always agree. So here we have uku. Now we are applying the properties of inner product. So we are getting, but now it's squared. So meaning you're going to get k squared uu squared. This one is not dark enough. Let's just go back to our usual thing. That's the left hand side. Now we are going to the right hand side, and on the right hand side we have so this one is the same as, but now for v we're making a substitution. If you use the inner product space, so we have some axioms of the inner product. We are going to get u and then this k. So you're still applying those axioms. Now we're going to have k squared. This is basically k squared. The norm of u is squared. So you can see the left hand side is equals to the right hand side. So that was step 2. Now we're moving on to the next. So in our third, so we are supposing that u is still not equals to 0, v not equals to 0. But then we have lambda u plus v, lambda u plus v. Lambda u plus v, but lambda is a scalar, so we're going to continue applying our rules. So this one is the same as multiplication when you're opening the brackets, but now it's an inner product space, so you're not going to interfere with anything. You open your brackets, but make sure everything remains in the inner product space. So we interchange. We're just playing with the rules with the axioms in the inner product space. So we also interchange. This will enable us to collect like terms. So we have lambda u, then v lambda u plus lambda u v v. So all these lambdas u, if you follow those axioms, you're going to get lambda u squared. This one is lambda vu. Here you're getting lambda uv plus vv. This is a quadratic equation, but before that we know that these two, according to the axioms of inner product, they're the same, so we can add uv. You're saying that vu, according to that axiom, is equals to uv. So when we're using this axiom as well, we are adding the two. This takes the form of a quadratic equation. So we're going to make our substitution that lambda is equals to negative uv over the inner product of u and u. So wherever we have a lambda, we substitute, but remember initially we had a 0, so we are using a bracket because we have negative values involved. Squared, wherever we have lambda, we're making that substitution, plus 2 negative uv we are multiplying by uv plus that vv. So when you simplify, you will open the bracket, this will become a positive value, so you will get uv squared over this u will be squared, but now it cancels out with what, so it remains u. This is positive, this is negative, it becomes minus 2 over, okay, nothing cancels out, so we're left with that. But you see, these and these are the same, so we can expand and then simplify. So this becomes over plus v and v. So if you check here, you realize these two are the same, and remember we have a 0. So if we subtract this, we will have negative u v squared plus v. But now we had a 0, so this will go on the other side. We are going to get a positive value. We are going to get u v squared is less than, so this sign here was less than or equals to, so we are retaining the sign. Now when you multiply both sides with this inner product, you're going to be left with uv squared is less than the inner product, and now that proves the Cauchy-Schwarz inequality. That is the proof, and then somebody can ask you to apply it or to verify. So we have a question here: verify the Cauchy-Schwarz inequality for the vectors u is equals to 1, 3, v is equals to 2, negative 1 in R2. So our solution is simple. If you ask to verify, it means you are supposed to prove that these two vectors fulfill this condition. So your first step will be to get the inner product of u and v. 1, 3, 2, negative 1. So you multiply 1 by 2, and then you add the same way we do for inner product. 1 times 2 plus 3 times negative 1, which gives us negative 1. And then next you get the inner product of u by itself. You will have 1, 3, 1, 3. That gives you 1 plus 9, which is 10. Then inner product of v and v. So we are getting 4 plus 1, which is 5. So our formula for the Cauchy-Schwarz inequality states that the inner product of uv squared is less than the inner product of vv. So uv is negative 1. Negative 1 squared will give us 1. So it's supposed to be less than u. It's 10 times 5. But 10 times 5 is 50. So 1 is less than or equals to 50, which is true because 1 is less than 50. But now in our case, okay, it's supposed to be less than or equals to. So in our case, we are getting strictly less than. So it satisfies the Cauchy-Schwarz inequality. Thank you for joining us. Bye. Let's see you at the next.